So how's everyone doing today? Hopefully everyone had a great day one. I know I did. I had a lot of great conversations, sidebar meetings, and we're really excited to get rolling on day two. Big thanks to our dinner host last night, 16 Stone. We had about 100 people have dinner last night, and it was just great. Perfect way to end the day. So as we get rolling into day two, really proud of the fact that we had so many great discussions yesterday and questions, and we're going to continue that today. I mean, that's what really makes this conference so good, I think, and kind of sets us apart from other ones. This afternoon we're going to be having a breakout session, so start thinking ahead at what session you want to go to, and get some questions ready or points for discussion with that. So as we get going today, we're going to have a brief welcome. So it's my pleasure to introduce the Chief of Staff for the 119th New York State District. She works in the office of Assemblywoman Mary Ann Buttonshawn's office. So please help me welcome Ms. Dana Nimey-Olney.
Good morning. The Assemblywoman's very sad she couldn't be here today. She loves coming here. She loves all this. I am a poor substitute and even poorer public speaker, so bear with me. So I'm just going to read something from her. Welcome to the Quantum for International 5th Annual Workshop here in the Mohawk Valley. The Advancement Center at Innovare brings a state-of-the-art and unique space for scientists from all over the nation and globally to research quantum science right here in Oneida County, Rome specifically. Our area stands out in the field of research, and it shows by the amount of people attending the conference this week. We are lucky to have such a wonderful facility of this type to work and research in the field that is emerging to be one of the top scientific fields internationally. The collaborations here between government, academia, and scientific industries will help to shape the future of Innovare and the future of quantum science. So again, on behalf of Assemblywoman Mary Ann Buttonshawn, I would like to welcome you all to day 2 of the 5th Annual Q4i workshop and thank Innovare, AFRL, Griffiss Institute, and all others to help make this conference a success for our community, and welcome our guests and attendees who have come from all over the world to Mohawk Valley right here in Oneida County. Thank you very much.
Thank you, Dana. We always appreciate the great support that we get from our Assemblywoman, Mary Ann Buttonshawn. She is just a tremendous, again, friend of the lab and supporter of AFRL and the Innovare Advancement Center. So, as we get going here in our tech program, please help me welcome Dr. Anderson Beraldo de Araujo. He is Assistant Professor of Logic at the Federal University of ABC in Brazil and holds a PhD in Philosophy from the University of Campinas and is a PhD candidate in Mathematics at the University of Minho in Portugal. His expertise is in the algebra of quantum computing and artificial intelligence, and he is supported under our AFOSR quantum reasoning system program. So it's an honor to have his presence here, given the long trip that he made here. Welcome. Thank you very much. Here's the down arrow. Advances. Thank you.
Good morning. Thanks for the introduction. Today I'll talk about large-scale simulations of quantum circuits. The actual title of my talk is Quantum Reasoning Systems, and I'm going to show you how this notion of reasoning about quantum computations in a way involves involves simulations of quantum circuits on classical computers. And this is a research under support for the ONR Global and for the AFOSR. and it's mentored by Dr. Kyle Gustafsson and Dr. James Lai, and to be developed as a research in the Iberian Nanotechnology Laboratory under the supervision of Dr. Rui Barbosa and Ernesto Galvão. And it's actually based on results of my PhD thesis at the University of Minho, supervised by Professors José Espírito Santo and Luis Pinto. My talk will have 6 short parts. I begin with the aim of, with a proposal. My aim is to perform simulations of quantum circuits in classical computers for large-scale capacity, meaning the product between the quantity of qubits and the depth of the circuits should be greater than 10,000. And for that, I think we need a different kind of mathematical approach, which I call synthetic algebra. Usually, quantum computing is from the point of view of programming is based on linear algebra, and I think we need a different perspective to be able to make large-scale simulations in classical computers. And the basic idea of synthetic algebra is that we can represent quantum operations with logical rules, so that we don't need to actually perform the numerical operations, and these operations can be delayed to the measurements, where we can make statistical sampling to estimate the probability distribution of the generated by the circuits. And I have basically 2 main motivations for doing that. The first one is it is impossible to do it. It's impossible to simulate quantum computing based on quantum circuits or other models on classical computers. But I think that, and I'm going to show you how to do that, we can do estimations, statistical estimations that are useful to represent what is going on quantum computations. And so we can overcome the exponential explosion of information needed to represent quantum states and quantum operations. And my second motivation is that actually already there are works that try to represent quantum computing using other mathematical approaches, not based on linear algebra, but based on category theory. But they are unable to represent the dynamic of the circuits. They represent statically what's going on a circuit. And I want something that can give us the real outputs of the circuits. I need a dynamic perspective. And I'm going to do that based on 4 steps. The first one is to represent linear algebra with a logical calculus. I give you a flavor of it now in a moment. And since I have a representation of linear algebra in terms of logical rules, I specify that for quantum linear algebra and define circuits in terms of categories. And in the third step, I define rules for actually getting the information of the rules that represent the states in quantum circuits. And finally, we perform statistical sampling to get the outputs of the circuits. There are some very interesting and notable simulators. Basically, for a group in Netherlands, they was able to simulate 48 qubit circuits for 48 qubits. Ellerbrock and Martinez from Stanford University, they showed how to generate circuits for millions of qubits, but not performing the computations. And also, 2 years ago, a Chinese team make simulations of quantum circuits for 52 qubits. This is the team that showed that the proposal of quantum supremacy made by Google Lab actually didn't work. They made that simulation. And finally, there is one other notable simulator by a German team. They are able to simulate 37 qubits. It's not like the previous simulators, but they made that on laptops, on CPU, based on CPU processing. And they use 3 tensor networks. And in a sense, it's not like the same approach that I propose, but it's also based on this idea of trees of networks that I'll show you. Before I give you some details about the approach, it's important to keep in mind that quantum computing from the point of view of programming is based only on 3 principles. The first one is that states are unit vectors in complex Hilbert system composed by tensors. From the point of view of physics, we have a continuous mathematics to represent quantum phenomena. For example, here is an illustration of electromagnetic radiation in terms of the contravariance between electric and magnetic field. But to program this, we make simplifications. No, it's not forming well. I don't know why. Here it's to be a vector. The qubit 0 is a vector with components 1 and 0, and the qubit 1 is a vector with components 0 and 1. And if we want to add new qubits, we use the tensor between them. And here is represented by the Cramer product. This is made not right. I don't know why it's generated that. Oh, I'm gonna have a problem. The second postulate from the point of view of programming is that the evolution, the change of the states, is based on unitary operators that in a way represent the energy operator of physical systems. But in the case of programming, these energy operators, the Hamiltonian, are just unitary transformations. They are rotations applied on the states of the states that are represented in the secrets. So here is an illustration of the NOT gate. It's a matrix with 2 rows and 2 columns. If we want to apply it to 2 qubits, we make the tensor product between them, and then we get a matrix with 4 rows and 4 columns. And this is the exponential explosion of information. When we have n qubits, we need n 2 to the n to describe them. But if we will look here, we see what the NOT gate do. It takes 0 qubits and gives us 1. And it takes the qubit 1 and gives us 1. We are not performing numerical operations. We are reasoning on that. And that's the key idea. We don't need to perform numerical operations to represent quantum gates. There is a logic of quantum gates which represent this idea. Of course, for the NOT gate, it's easy. It doesn't involve complex numbers, position of states. How we do that for a universal set of gates for quantum computing? And finally, measurement are projections that give us states probabilistically. And here it's also represented by matrices, but it's a complex operations from a logical point of view, because it's collapsing the state of the basis of the system with a certain probability. And that's all. We have just 3 postulates, and based on them we define the gates and try to discover circuits that make interesting things. And that's the hard thing about programming. We have simple tools, but we want complicated objects to be done. And here is an example of the circuit of the Deutsch algorithm. And here you have below the formula that represents this circuit in the algebraic system that I have tried to develop. And basically all that I try to do is how to decompose this formula that represents circuits in terms of logical rules that from the one side give us the representation of the operations of the circuit, but without actually performing the arithmetical operations. So I do that with two steps. One is syntactical and the other is semantical. And here is a compact way of saying that the syntax of the system has symbols for scalars, for vectors. Here, so let me show here. The scalar, so the system is able to represent complex operations, operations on complex numbers. And here are symbols to represent operations on matrices. And the novelty here is an idea of representing matrices in terms of the number of rows and columns, and a formula that describes the operations made by the matrices. And here are some examples of the rules to perform the decomposition of the formulas in terms of logical rules. The important here is that we have a notion of equations between formulas, which is based on logical rules. Let me give you an example that maybe is more helpful. The idea, for example, I want to prove the distributivity of the matrix product over the vector sum between matrices, sum between matrices. In this system, we do that. So I want to show that this is equal to this. The product over the sum is equal to the sum over the products. I want that to be an equation. So in this system, I put one formula as an input and try to logically get the other formula as a tree that represents a proof, a logical reasoning. And if I can do that in one direction and I can do that in the other direction, they are equal. And here is an example. I'm not entering into the details. And here I'm showing that both formulas are equal without making numerical operations, just by logically reasoning on the rules of the algebraic, linear algebraic operations. And this is the syntax. It's made of a lot of rules for that, in that way. And the semantics, the meaning, what's the meaning of these abstract rules? These are rules to manipulate symbols. And to this symbol correspond categories. And we are able to prove that whenever you have an equation that expresses a fact, a linear algebraic fact, we have a proof of this equation based on this kind of rules here. And this is possible because linear algebra is actually an equational theory. It's based on our ability to think about equations. And to do the proof of that, I perform transformations of the symbols in terms of categories. Category theory is all about this kind of diagrams. Here, for example, if I have a matrix Fm, a matrix M and a matrix N, I transform it in a formula F, and the matrix M has M rows and N columns, the same, and the matrix N has P rows and Q columns. Then when I perform the tensor product between them, this means that I'm making the product between the natural number that represents the number of columns and the number of rows. And so we always think in terms of quantum operations without actually touching the cells of the matrices. And since we have a way of representing the operations of linear algebra, and specifically the operations of quantum linear algebra as categories, we can think about the quantum circuits as categories in itself. A quantum circuit corresponds to a category where the objects are the states, the transformations of the input to the output, and the morphisms, the change that we made in these states, are represented by formulas in this algebraic system, this synthetic algebra. And so to make optimization of circuits is actually to perform a functor, what we call a functor. A functor represents the way that we can change an operation. It's a function. I have a structure and I have another structure and I would like to change it to another one. This change is represented by a functor. It has a structure. And so when I want to optimize a circuit, I want to minimize the number of gates, the number of measurements. So I'm actually applying from this perspective a functor over the circuits. And then if transformations, optimization of circuits are functors, we can also ask about how can we change our optimizations. This is what we call in category theory a natural transformation. It expresses how much I can change my optimizations, my functors. And here I'm able to prove that the number of morphisms, the number of gates and measurements that I can do to optimize my circuit depends only on the number of the objects, the states. And for that, I applied the version of Yoneda lemma. That's not important here. Basically, the idea is that if I have a circuit, I want to optimize it in another circuit D, then I construct an algebraic circuit that represents all the possible ways of optimize it. And then there is a direct path between them, and applying Yoneda lemma, all the possible transformations between this and this is actually given by the functors, the optimizations that I try to perform. We say that the diagram commutes, both paths are equal. It actually isomorphic. Well, fine. This is a little bit abstract. Can we get something concrete to actually perform the operations to represent the computations of quantum circuits? I said in the beginning it's impossible. There is a Mandela say it always seems impossible until it's done. Here I gave you a flavor of the mathematics, and then I try to implement that to see if it actually works. And as I said, I also introduce rules to represent the actual information of the circuits. Also there is rules for measurements. I have not showed that here. And so finally we make a statistical sampling to get the results of the circuit. And I implemented that theory in Rust, system programming language, which is able to be extended to VHDL language. Because I have applications in mind here, and I also implemented this statistical sampling, and implemented some basic algorithm for cryptology and neural networks and SAT solvers. And especially for this meeting, for this workshop, I performed the calculations, I made the simulations, because it's my first time here in the US, and I would like to try to keep this American idea of innovation. And then here is the data. I implemented circuit for quantum Fourier transform in this library in Rust, and here is the data about 100 qubits simulated in my personal computer. Here you can see that this get at most 3 minutes, and you have here data about the time generation of the circuit, how much time it's needed to represent the circuit in terms of single algebraic formulas. Here it's always the scale of milliseconds, microseconds, and here the time needed to actually transform and to get the informations of the states of the quantum circuits, which is a polynomial with a very large exponent, but it's not exponential. And let me give me some more details to you to get what's going on. Here's the data about some samples. You can see here in the number of qubits, it's a polynomial in the number of qubits, the time needed to be processed. And here in the once I have this the formula that represents the circuit, how much time I needed to get the information that represent the states in each step of the circuit. And here you can see it's actually an n log n on over the time to generate the circuit. And that's it. What we can do with that? Well, the third prospect that I have in mind is to empirically determine how much capacity we need to perform Shor's algorithm in a way that he can break the RSA scheme. This is an open problem. There is some mathematical estimations, but they are based on asymptotic behavior of the circuits. I want to do that on numerical data to calculate how much capacity we need to break to RSA scheme. I also think that this could be very interesting to perform neural networks with SAT solvers, because we have a kind of logical theory about the behavior of the quantum gates and measurements. And I also have some algorithm implementations about neural networks, combining them with SAT solvers. And I have that in mind because I think that neural networks, the combination of neural networks with SAT solvers could be important to get new algorithms in the line of Shor algorithm. And finally, I think that we know that in defense science and technology, we have a lot of implementations of circuits, usually made in VHDL. We know that we can transform classical circuits in quantum circuits. And with this kind of simulation, with this kind of quantum reasoning, we can transform the circuits that we already have and to combine and to get estimations for large-scale quantities of qubits and try to discover new algorithms and new applications. But for doing that, of course, this is not be able to do in personal computers, we need parallel processing. And I think that implementations of this library in FPGA is a good way to do this kind of application. Here I just showed you some ideas, but as Turing said, this is only a forestate of what is to come and only the shadow of what's going to be. I would like to thanks for the Q4i organizers, the participants, especially Kyle and James, especially Jim that was make me able to be here today, and my supervisors at INL, Rui and Ernesto, my PhD supervisors, Professor José Espírito Santo and Luis Pinto, and especially my family, Viviane and Anthony are there in Brazil, And here it's a diagram, it's a categorical diagram made by my son. He is 6 years old. I was working about the implementation of this system that I showed you the data. And he was hungry, and we would like to buy pizza. And he asked me how much time I needed to finish and to get the pizza. And then and he was sad. And I said, oh, we need to keep ourselves happy, because then we are going to get the correct math. And if I finished here, we will get the pizza. And then he take his pencil and paper and made this diagram. If we are happy but turn out to be sad, we get the wrong mathematics. And if we are happy, we get the right mathematics, and we also get the pizza. But curiously, here it's not a category, because it's not the same way to go in that way and that we get the wrong, and in this way we get the right. But there is a category which goes from here to here, from the right mathematics to the pizza. It's lacking a morphism. If we add these morphisms, we get the right things. We get the right mathematics, and we get the right applications. And this morphism, I think, is collaboration, co-working, working together with the others. And for that reason, I'm here to collaborate and to make this a category, to make the diagram commute here. Okay. Thank you very much for your attention.
We have time for questions. We actually have a few minutes for our next speaker live. So
feel free. Hey, thank you for your talk. I also work day-to-day simulating quantum systems, so a lot of what you spoke was very relevant. And yes, the cap is around 30 to 60 qubits, where classical computers struggle. So question for you was kind of a point of clarity halfway through your talk. Does your sin algebra approach, can it produce amplitudes that a quantum circuit would yield at the end? So the complex numbers of every binary state? Or, and the reason I ask is because you also showed that you do statistical sampling, which could yield, say, the probabilities of finding certain states. So I just want to know, does it also produce the amplitudes, if that's what you're interested in?
Thanks for your question. It makes both. It's actually, let me go. The formulas, they store the information that represent the state of the system. Here there is a formula in the beginning that represents the input, and the application of the gates give you another layer. But the application of the gates is represented by rules, not by matrices. And these rules keep the information about the amplitudes. It's very strange, I know, that we are keeping the information about the state without actually doing the operations. But this is possible. This is the way that we think in category theory. And for that reason, I gave you that example, that diagram here for my son. Because he is in a way thinking about what's going on. But he is not actually doing the calculations. It's abstract way of thinking, of transforming data. And it's exactly that idea that I use in the case of quantum circuits. So you keep the information about the amplitudes until the end, and this can be done efficiently. And in the end, you have a formula, a logical formula. You don't have a vector, a matrix, you have a formula. And you need to parse it to get the actual probability density, the distribution that the circuit generated. And in that point, There is also rules that represent measurements in terms of this SIN algebraic approach. And then you make statistical sampling, because you don't need a knowledge about all of the distribution. You need specific information about some amplitude, some probabilities, some amplitudes of very specific outputs, because you want that the algorithms give you specific outputs. And this can be done. And the more information we want about the probability distribution of the circuit, the more processing we need. And for that is the power of quantum computing. But we can get useful information about this distribution without actually representing all of the whole distribution, just some specific output.
Thanks for the talk. This is interesting to see category theory in the space of quantum mechanics, so thanks for that. I'm curious a little bit about the implementation that you chose with putting these formulas in Rust, and then why you think implementing on FPGAs is the right way to go. So if you could speak a little bit about that.
Okay, thank you. Why Rust? Because Rust is the unique system language which has a correct approach to concurrent programming. And we need parallel processing to get useful information about the distribution here. So I need to program in a system programming language, and so I have basically three options: C, C++, or Rust. But C and C++ don't allow me to work correctly with concurrency, and we need that when we are talking about high intensive processing for quantum systems. So Rust is the best choice. But Rust already is very high high level programming. We need to go down to the circuits. And for that reason, I think we need FPGA implementations, because we can also do with GPU, using as the AI industry has done, make parallel processing with GPU. But we know that in defense military applications, we have a lot of implementations of FPGA and a lot of libraries and circuits implemented in VHDL. So let's take that and transform it to quantum circuits and make the simulations and try to discover new algorithms. That's the idea.
Thanks.
Hello. Thank you for the wonderful talk. So my questions maybe is a step or two down the road, because I'm not sure exactly what logical gates you're working with. It'd be great to talk with you afterwards. But have you thought about applications with variational algorithms? In my mind, I see a category from parameter space to the space of unitary operators, and then connecting that to circuits and going from there. Has that been something that's crossed your mind, or has anybody ever looked at those?
Yeah, thank you. Yeah, it's possible to make the adaptations for a variational algorithm, because it's actually a question about how we can extend these formulas, these algebraic formulas here, like that, putting new parameters. That's it. If we want a specific kind, for example, variational algorithms to be represented here, we extend the formulas with data about that parameters. That's the idea. But then we need rules to generate the rules like that with the parameters. I have not done that yet, but it's possible. But it's possible, and that's the way that we go. We add parameters in the formulas to do that, and then create rules like that represent the parameters.
Do you think that functors would be the way to help define the optimal algorithm with the optimal parameters?
Yes.
So that would be a way to, be much more easier than gradient descent.
Yes, yes.
I'm going to hit you up after this. Thanks.
Okay. Thank you for it.
Hello, thank you for your talk. I really appreciate this new formalism, and I was wondering, can it be used to find categories of tasks that have a large quantum speedup?
Sorry, can you repeat? I didn't hear.
Oh. Can this formalism be used to find categories of tasks, algorithms, that automatically have a quantum speedup?
Yes. I actually made some algorithms for optimization of circuits based on the category that underlies the circuit. I have not showed here, and for that reason I needed this theorem here. Because as I know that what is important to define circuits, quantum circuits, from the categorical point of view, as I know that only the states matter, only the states, meaning, let me here, only the states here, and the state is the meaning of a formula. It's not actually a vector. So I can take the formula, and the formula has a category interpretation like this, and then I use category theory, properties of the diagrams, to see how I can optimize the circuit. How can I get new categories, because the circuits are a category itself. And then we can make algorithms based on category theory. This is completely different from the usual way that you use category theory in math. In category theory, there is a joke, and category theory is abstract no sense, because it's very abstract and no meaning at all. But here I'm using this abstract no sense to make sense of the circuits, and it can be done.
Okay. Thank you very much.
All right, great. Thank you so much. And it's a great talk. Thank you for the questions. Let's thank our speaker. All right. We now have the privilege of hearing from Dr. Claire Cramer, the Department of Energy Program Manager, who will present the Department of Energy's Quantum Center overview and share some thoughts on the way forward and progress they've made. And we really want to thank Claire for taking time out of her busy schedule, not only to get here, but she literally came from another talk that she was given virtually and arrived here just now. So Claire, thank you so much.
Well, it's a pleasure to be here this morning. I've always liked upstate New York, so this is good. Let's see, that's me, and this is my talk. So I'm going to talk about quantum information science, and specifically our National Quantum Information Science Research Centers at the Department of Energy Office of Science. So we are the nation's largest supporter of basic research in the physical sciences. We support scientific research directly. We also direct the support of development, construction, and operation of unique open access scientific user facilities that are made available freely to external resources, researchers rather. That's what we do in the Office of Science. We support basic research with direct funding and also with facilities and infrastructure. Our mission is to deliver scientific discoveries and major scientific tools to transform our understanding of nature and advance the energy, economic, and national security of the United States. We support tens of thousands of researchers at hundreds of institutions and our 17 national laboratories. In the Office of Science, we steward 10 of the 17 DOE national laboratories. We support tens of thousands more users of our scientific user facilities, and our current budget is just over $8 billion. So we drive discovery science for the nation through direct support of research. We foster great minds and great ideas always looking to bring America's brightest minds into this endeavor across multiple disciplines at universities, our laboratories, and other research institutions, and we provide unique world-class facilities. So this, I keep saying we have all these people that we support and all of these laboratories. This is where they are in the United States. So highlighted on this map with the gold stars are all of the institutions that we support with research funding. The dots are DOE laboratories, so we have 17 of them. The blue dots are the 10 DOE laboratories that the Office of Science stewards. We actually fund research at all of the laboratories, and so the ones that we don't steward are the red dots. Yikes. There we go. So, what types of science? I said we're the largest funder of physical sciences in the United States. We divide that into 6 program offices. So I'm from the Advanced Scientific Computing Research Office, and so what we do is deliver world-leading computational and networking capabilities and fund research to extend the frontiers of science and technology. We also have an Office of Basic Energy Sciences that you can read their official descriptions. I'll give you colloquial descriptions. So it's a lot of chemistry and materials science and characterization capabilities. Biological and environmental research is a lot of Earth systems modeling. Fusion energy sciences, we're looking at the energy production side of fusion, not the other sides of fusion. We have a higher energy and nuclear physics programs that look at the fundamental interactions of matter and the building blocks of the universe and good stuff like that. So those are our sort of research organizations. And you might ask, how does that relate to quantum information science? Quantum information science does not map cleanly onto any of those 6 qualities. So back in 2015, 2016, when we were looking at building a new quantum information science program in the Office of Science, we looked at 2 different things. So we first looked at what contributions we could make to advance the nationwide QIS enterprise. So what expertise do we have, what tools do we have that can be brought to bear on this national activity? And then we looked at where quantum information science might have a potential impact on our mission areas. So looking at applications of quantum computing that are relevant to computational science, looking at quantum networking in ways that can advance the scientific endeavor, looking at sensing applications that can help us understand the fundamental properties of our universe better than we do now. So we knew that we were relatively newcomers to the field when we started all of our investments. Our first investments officially in quantum information science were in 2017. So others had been doing that for decades prior. So we said, okay, what do we bring to the table? And what does this bring to the table for us? And we looked at our unique strengths. We solicited input from the community. We wanted to leverage investments we had already made, and we understood that the QIS effort would be cross-cutting. So if you look today, QIS crosses the technical breadth of the Department of Energy's Office of Science. So in the Advanced Scientific Computing Research Program, which is OSCAR, we're looking at algorithms, we're working at software, we're looking at workflows, we're looking at hardware test beds, we're looking at computing models. In basic energy sciences, they're looking at systems and computing applications for chemistry and materials. They're looking at infrastructure and characterization tools, and they're looking at basic questions of coherence and entanglement in mostly solid-state systems. In biological and environmental research, they're looking primarily at imaging and other sensing applications, and they're also considering computing applications that may be relevant to them. Similarly, in fusion energy sciences, they're looking at qubit synthesis, quantum computing for plasmas, and sensing applications that may suit niche needs of fusion reactors. In high energy physics, they're looking at quantum sensors, systems, computing, and sensing applications that actually give you insight into what dark matter and dark energy and new particles may be and how they're interacting with other things. In nuclear physics, they're doing something similar, looking at sensors, clocks, particularly clocks with nuclear transitions rather than electronic transitions in atoms, and applications of computing in their mission space. And then we have another program, so it's not one of our core research programs, but it's arguably more important, at least equally important, is the isotope program. So DOE's Office of Science isotope program is tasked with understanding the nation's needs for isotopes and ensuring a supply of critical isotopes that aren't available in the private sector. So they do research in isotopes, they ramp up production, and they study production capabilities. And they have been keeping an eye on bottlenecks for QIS in their space and are in fact ramping up capabilities. So they are not one of the core research programs in the Office of Science, but they are actually integral to our QIS efforts as a whole. The cornerstone investment that we have right now, thanks to the NQI Act, is of course these 5 national quantum information science research centers. They're all led by Office of Science laboratories and of course involve dozens of other institutions. So we have QNET, the Next Generation Quantum Science and Engineering Center, led by Argonne National Laboratory with David Oshalom as the director. We have the Co-Design Center for Quantum Advantage, or C2QA, led by Andrew Hauk at Brookhaven National Laboratory. We have the Superconducting Quantum Materials and Systems Center, or SQMS, led by Anna Grassolino at Fermilab. We have the Quantum System Accelerator, currently led by Rick Muller. This is a partnership between Lawrence Berkeley National Laboratory and Sandia National Laboratories. So Rick is from Sandia, but the lead lab is Lawrence Berkeley National Laboratory. And then we have the Quantum Science Center, which is led by Travis Humble at Oak Ridge. The centers bring together collaborations of over 1,200 people, roughly half of whom are students and postdocs. It's very difficult to have a slide that actually is current on the number of participating institutions. I believe we're actually up over 90 academic, industry, and national science institutions now. Those span 24 different states, plus the District of Columbia, and we have partners or funded partners in Italy and Canada. So, of course, there are unfunded affiliates or institutions making in-kind contributions who aren't counted in this list. So you can see where they are located in the United States. So through these institutional partnerships, the centers unite unique capabilities, expertise, and facilities to answer fundamental open questions in quantum information science, to leverage the 28 DOE user facilities, to train a new and diverse quantum workforce, to accelerate the cycle of technology transfer from discovery to commercialization, to accelerate scaling up in production, and to develop national standards and roadmaps for quantum technology that incorporate processes, metrology, and testing data from the research that they're doing in all of these institutions. It looks a little bit different when you put the institutional logos and not rather than showing dots on a map. Of course, the dots on the map are large, and sometimes one dot covers multiple institutions. So you can see that 10 of our 17, or 11, I think, of our 17 national laboratories are participating in some capacity, as well as other laboratories that are outside the DOE ecosystem, such as NASA and NIST and INFN in Italy. You can see dozens of universities as partners, as well as I think we are up to 19 industry partners. So it really spans a lot of types of institutions, a lot of types of research, and a lot of types of applications. Each center tackles major scientific and technological challenges in QIS in unique ways. It may sound like all the centers are doing the same thing if you just list at a high level what they're doing and what they're working on. But each has its own unique portfolio of research that spans the technical area of materials, computing, communication, and sensing, among many other things. They're working together, and in fact the center directors meet at least monthly, if not more than that, to advance the broader field of QIS and ultimately the readiness of quantum technology. I just want to highlight a few of the key elements of each center. So at the Quantum Systems Accelerator, they're developing new prototypes of quantum hardware to test the principles of quantum computing. So today's quantum hardware is noisy. The QSA is developing algorithms for key applications that in areas that can be tailored toward error-prone environments, including calculations for material science and fundamental physics. They have a soup-to-nuts approach that looks at three main technologies useful for quantum computing and simulation, so trapped ions, neutral atoms, and superconducting circuits. At the SQMS, the Fermilab Center, they're taking a complementary approach by developing quantum computing based on superconducting materials that are tailored towards high-energy physics problems. So they're using their ability to design new hardware devices to mitigate and negate the effects of loss and errors as a means of tuning the performance. And they're also developing unique qubit-based quantum sensing platforms to identify dark matter and other things. A similar essential principle of co-design is being developed at C2QA, the Brookhaven-led center, where they're integrating advances in hardware, software, and algorithms toward establishing quantum computational advantage. So what C2QA is doing is doubling down on the superconducting approach to quantum computing and breaking it down and saying, can we make a 10x improvement in each of the component pieces of that would be required for a quantum computer that gives us a true advantage over classical computing. At QNext, they tackle the fundamental problem of how quantum information can be reliably stored, controlled, and distributed over quantum communication links. This is a fundamental step towards the development of quantum networks, which require advances in materials as well as optical technologies. So you see a picture there representing the electronic incoherence properties of spin defects in silicon carbide, which is one of the materials platforms they're looking at. And at the Quantum Science Center, they're developing materials for efficient and scalable quantum technologies that are naturally resilient to errors. By advancing the synthesis and fabrication of quantum materials, they will be able to support the long-term development of quantum computation and quantum sensing applications. And what they mean by all of this is that what they want qubits that are inherently resilient to noise. And so they are looking at materials that could support topological approaches to quantum computing. And in fact, Microsoft, which you may have seen a press release from recently, is one of their research partners. So just a handful of the achievements that they've made in the 2.5 years since we've initiated them. They've set a record for qubit lifetime in both quantum computing and quantum networks, preserving qubit coherence for more than 5 seconds, and paving the way towards more useful quantum applications and a distributed quantum internet. They have released numerous open source software products and even some open source hardware products to democratize access to the tools necessary for scientific progress. They have developed a 256 qubit programmable quantum simulator, and they're using it for new applications on a daily basis. They have captured a first ever appearance of a previously undetectable quantum excitation known as the axial Higgs mode. So that's one of those high energy fundamental physics applications that you wouldn't have thought qubits were relevant to, but in fact qubits are phenomenal sensors. They have discovered new nanostructural deficits limiting the performance of quantum devices. In addition to scientific and technical advances, they're also developing new tools and databases. So one of the very exciting capabilities they're bringing online now are 2 quantum foundries aimed at fabrication of different materials and qubits and devices relevant for quantum information science, as well as the characterization of those materials and qubits and devices. So in fact, there's a new foundry at Argonne National Laboratory with a sister foundry at SLAC in the Bay Area that we just had a ribbon cutting ceremony on probably 2 or 3 months ago. They've also established a national scale task force to evaluate qubit performance, build devices, develop standards for next generation devices, and consistently fabricate high performance qubits. The centers, of course, are advancing technology transfer, they're advancing science and technology. They also have a mission in ecosystem stewardship. So a large part of this is workforce development. So all 5 centers have locally launched summer schools. They've engaged with high school, college, and graduate students to help them understand what QIS is, to help them engage in the range of opportunities that are available to them, and help bring them into the QIS community and future workforce. Together, the centers sponsor an annual career fair that had more than 900 registrants in 2022. So we've been seeing increased registrations in each of the 3 years that the school has been planned. I think there's still time to register for the 2023 school. What they found is that it's about 27% undergraduate students, 39% graduate students, and 10% postdocs. They have a virtual vendor expo with a total number of exhibit booth visitors over 4,000, and over 100 registrants have applied to jobs directly from the QIS Career Fair platform. So this career fair is open to participation from anyone. It's put on by the QIS centers. Anyone can be a vendor at this. So I would encourage all of you to participate, to encourage your students and postdocs to participate, and those of you who are on the lab and institutional side, participate as vendors. We also have an element of ecosystem stewardship aimed at planning and coordination. Sometimes that means educating not just students and doing public outreach, but doing outreach to the community in government and in the national labs. So, for example, our center has held a workshop with the Federal Lab Consortium to highlight the value of QIS investment, to help people understand what this field is all about and the potential that it has, and to highlight areas of potential partnerships and help people understand specific applications of quantum algorithms. They've participated in road mapping exercises, so they've mapped the quantum relevant capabilities at the national lab user facilities and DOE quantum testbeds for the QIS community. So one thing we've found as we have brought our large DOE enterprise into the field of quantum information science, we need to connect communities who haven't traditionally talked to one another very well. So we have 28 user facilities, all of which have world-class tools for doing whatever it is that user facility is set up to do. Those facilities haven't connected very effectively with the quantum information science community. So our centers are trying to take a leading role in establishing those connections and helping, on the one hand, the QIS community understand how they can utilize these resources, which of course are available to anybody on a merit-reviewed competitive basis for free. So it's important that the QIS community know what these resources are, how they're applicable, and how they can gain access to these resources. It's also important for the facilities to understand this new application space, and we've also sponsored some tools development where research at some of our facilities has led to the development of new tools that are now deployed and available to the community at those facilities. This is a two-way street that our centers are facilitating. We've convened meetings of chief diversity officers of the center's host labs to make sure that we're using effective practices and constantly on the ball in terms of creating a diverse workforce for the emerging quantum industry. If we only pick the same types of people, we will limit our talent pool artificially, which is to the detriment of the whole enterprise. And finally, they're constantly participating in scientific sessions at major meetings across the United States. So, for example, at the 2022 AAAS meeting, they had a panel speaking about what they're doing and the broader impacts of QIS in society. They've subsequently had similar panels at APS meetings and other professional society meetings. So ecosystem stewardship is also a very important element of what our centers are doing. What do they plan to do? They still have another 2.5 years of funding left. Well, C2QA plans to find tenfold improvements in qubit materials, device performance, software requirements for useful quantum computing. QNext is going to, that's the one in Argonne, it's going to install a silicon solid-state testbed from Intel. So eventually, this is something that you should all pay attention to. What they would like to do is have external people come and help Intel put this testbed through its paces to really understand how effectively the solid-state platform works and what it's beneficial for. The Quantum Systems Accelerator, QSA, at Berkeley and Sandia is going to continue exploring paths for meaningful quantum advantage using lessons learned from each of its 3 technologies that it's considering. The Quantum Science Center is going to develop roadmaps for quantum materials and quantum devices based on primarily topological materials, but others as well. And SQMS at Fermilab plans to deploy a quantum computer prototype in a newly commissioned quantum computing lab. And that machine will be specifically co-designed for advantage in high energy physics quantum computing applications. Okay, so these 5 centers are impressive. They're a significant investment, so it's $125 million a year for 5 years, spread equally among the centers. That's not all we're doing, and it's important to understand that those centers sit in a context within the Office of Science. So I want to take a moment to talk about our core basic research and infrastructure, which forms the groundwork for all of our more specific and infrastructure-based QIS investments. So we have core research programs in all 6 of our program areas, plus isotopes. And just some highlights, we have harnessed the power of what was at the time the world's fastest supercomputer, that was the Summit supercomputer at Oak Ridge National Laboratory, to compare to Google's quantum device to assess whether it had actually achieved quantum supremacy. We achieved a first high-fidelity teleportation of a light particle using sensors originally developed for cosmological observations. We have been able to demonstrate really clearly the effect that cosmic rays have on superconducting circuits used for quantum information applications. So one thing we have that's a little bit unique at the Department of Energy is deep underground facilities. And deep underground facilities at different depths that allow you to study the impact of cosmic radiation systematically. So that's something that we discovered and have continued to do. We have captured for the first time interaction between dynamics of noise on the fidelity of quantum calculations. And we've, at this point, launched several quantum network demonstration projects at several laboratories. So Berkeley and Argonne have the lead on those, but we also have participation from Oak Ridge, Fermilab, and Brookhaven. So in the future, plans for our core basic research, we really want to fully leverage the diversity in our funding modalities. At DOE, we're able to fund very small programs, right, ranging from a summer or 3-month graduate internship at a DOE laboratory, where we have a program that allows graduate students to propose that to us, and we will provide them with funding to do a portion of their thesis research at a DOE lab, so ranging from a few months to really decades, where when we invest in these large-scale open access user facilities, we don't do that planning to shut them down in just a few years. So in the range of month to decades, we want to make sure that we're leveraging the diversity of programs that we have to offer. We want to make sure that our programs are agile enough to keep up with this very rapidly moving field. We want to continue to provide more resources to incentivize the community, and we want to build on and expand our existing infrastructure. So what is our existing infrastructure? I referred to it many, many times. So we have 28 user facilities in the Office of Science. I want to highlight a few of them here that are specifically useful for quantum information science. So we have hard and soft X-ray light sources to probe atomic and electronic structure. We have several of these. So we have a large free electron laser at SLAC, and we have synchrotron light sources at Brookhaven and Berkeley. We have class 10, 100, and 1000 clean rooms for device fabrication. We have lithographic etching and deposition tools, and optical, electron, and scanning probe microscopy technologies, and nanostructure characterization tools. So those are at our nanoscale science research centers. There are 5 of those. They are, so in contrast to our light sources, which is a large kind of monolithic facility that has a difficult and costly capability, the nanoscale science research centers are aimed at collecting useful tools regionally that are accessible to people who may not have such an expansive suite of tools or a unique suite of tools available to them at their home institutions. So there are 5 of these. They're distributed at laboratories across the entire nation, and those are the ones that are really have a lot of capabilities for microscopy, for lithography, etching, fabrication, and growth. They also have theory resources. So if you're good with the materials and experiments but need theory support, they also have that as an available resource. And finally, we have our high performance computers. So we have 2 leadership computing facilities, one of which has recently been announced as an exascale machine. We're eagerly anticipating the machine at Argonne also achieving its exascale design feature. And we also have NERSC, a capability quantum computer, or sorry, a capability classical computer available to DOE researchers at Lawrence Berkeley National Laboratory. So we have this vast suite of tools that already exist. We're always looking at ways to upgrade them and make them more relevant. And at the same time, we're building a unique DOE QIS infrastructure. So those 5 nanoscale science research centers have internal research to develop new tools, some of which are already rolled out. We have 2 quantum computing test beds that give you sort of bare metal access to novel quantum devices. So at Lawrence Berkeley National Laboratory, we have a superconducting qubit platform. And at Sandia National Laboratory in Albuquerque, we have a trapped ion platform. And those are also available. They're not large and formal like the user facilities are, but they are available for collaborative research on a merit-reviewed basis. And these give you deep access to the guts of the quantum computer. So if you want to try out a new compiler, if you want to look at ternary rather than binary logic, if you want to look at different types of gates and novel pulse sequences for gates, these test beds will allow you to do that research. So we put those in place just about 5 years ago. It took a little bit of doing to ramp them up during COVID, but now they're going strong. And we hope to expand those capabilities in the future. We also, sort of on the flip side of that, have a quantum computing user program that provides access to cloud-based industry platforms. So we look at both sort of the ground up, what future capabilities are on the bleeding edge that haven't yet been incorporated into those well-engineered, robust industry platforms that are available on the cloud. And we provide access to the cloud resources from vendors. So in the future, and we hope that the CHIPS and Science Act authorization will turn into an appropriation that we can use to grow these programs. We want to broaden access to these emerging capabilities and explore possibilities to provide access not just to quantum computing platforms, but possibly also components and smaller devices. On the isotopes front, we need critical isotopes to do all of these things. Our domestic capacity does not even meet the current demand, and we are often dependent on foreign sources. So our isotopes program has been expanding its investments to create new capabilities. So at Oak Ridge, for example, they're building a stable isotope production and research center, which broke ground late last year. And we want to make sure that we're reducing dependencies on foreign or insecure isotope supply chains, and that we understand what the research needs are going into the future for quantum information science, so we're prepared and we don't fall behind for a lack of supply. We have, in addition to the workforce efforts at our quantum centers, we have additional workforce development programs at the Department of Energy, so the demand for quantum workers already outpaces supply and it continues to grow. So we have a computational science graduate fellowship that for many years now, so the program itself is over 30 years old, but increasingly we're seeing applications in quantum computing, and I would encourage those of you who have promising graduate students to have them take a look at this program and see if it might be a good option for them. We have industry partners expanding the range of student opportunities that we're able to offer through the National QIS Research Centers. And we have a broad range of summer schools. So some of which I highlighted are sponsored by our centers, and some of which are sponsored by our laboratories or directly at headquarters. We have new funding opportunities. So Renew, reaching a new energy sciences workforce, and FAIR, which is our Fair and Inclusive Research Program. Those are designed to build capacity at institutions and within demographic groups that typically the Office of Science has not funded, or historically the Office of Science has not funded. So Renew is aimed at providing opportunities for students at all levels, and FAIR is aimed at providing opportunities for faculty to establish research programs at new institutions. So I hope that you can see that quantum information science at the Department of Energy is a long-term effort. We have made investments that have enabled steady progress on a number of fundamental technical fronts. QIS is now embedded across all 6 of our core research programs. So we have QIS-specific funding opportunities and also QIS within our other core research programs. And we anticipate this multi-pronged strategy only growing into the future. So we have core basic research, center-scale efforts that facilitate public-private partnerships. We will continue to develop our infrastructure, critical supporting technology, and our workforce. So thank you very much for inviting me to share our programs with you and talk about our centers. And I think at this point I'd be happy to answer any questions anyone has.
Hi, Claire. Is this thing on? Yes, okay. Very great talk. You had the unenviable job of describing all of DOE's mandate over quantum, which is, impressive that you can cover so much material. I have a question about one of DOE's core strengths, which you didn't talk a whole lot about, which is the user facilities built around HPC. And I guess I come from the perspective that, a lot of us are building the quantum hardware. And even if we achieved our dream very quickly and we built a very capable quantum computer.
Okay, so we need to stop for a sec. I know you're speaking into a microphone, and my guess is that they can hear you really clearly. I can't, because I think I'm behind the speakers.
I see. Can you hear me better if I just shove my mouth next to the microphone? How's that?
A little bit. So you said something about user facilities.
Yeah, so one of DOE's core strengths are the user facilities, and it's really around HPC centers, right? Exascale computing and so forth, NYSTEC and Oak Ridge.
Yeah.
And one of the strengths in those facilities are the scientists that actually connect the dots from applications to the usage of HPC hardware. We who are making quantum computers think that even if we were wildly successful and achieved our aims of making very large-scale quantum computers that really could solve real challenges, one of the other challenges that we have is that nobody would know how to use them. Right. So I'm interested to know if DOE has any plans in kind of using that core strength in the HPC facilities where you have scientists who literally concentrate on those kinds of problems. I'm thinking at NYSTEC and so forth. Mm-hmm. And creating user facilities around quantum computing, using what we have today to try to get that workforce development where we can understand how to connect the dots to the applications. And are there efforts, underway at ASCR to utilize that key resource, or what are the plans going forward?
Right, so your question has 2 parts, right? So the first part is about co-design and making sure that you have kind of a soup to nuts solution from the hardware up through all of the applications, right? And then the second part of your question is, how are we leveraging expertise at our HPC facilities who understand very deeply how that's worked in classical computing. So we're looking at both things. They're not connected yet. And the reason they're not yet connected is that quantum computing hardware is really in very, very early stages. So the quantum computing hardware that we have now is not able to run useful applications, right? So even the largest quantum devices that IBM and their competitors are bringing into existence and making available are not able to run very deep circuits, and they're not able to run very many circuits at the same time, okay? So because of those limitations, what we're doing is, mostly through our quantum centers, but also through our core research programs, trying to iterate through as much of that co-design stack as we can using the small devices that are available today. So we have research teams that are integrated across the thrusts, for example, at the Quantum Systems Accelerator, where they have hardware people, they have software people, they have applications people, and they meet regularly and plan their scope of work so that the hardware as it's being developed and all of the layers of the software stack are developed in a way that has applications in mind and has the use cases for that quantum computing platform deeply embedded. That is right now a basic research effort. At the same time, right, as you point out, it's really important to bring in that expertise and that more operational expertise at our HPC facilities. So the two facilities that have the lead on this are the Oak Ridge Leadership Computing Facility and NYSTEC. So why have we left out Argonne? That's because Argonne has the lead on AI, which is an equally big deal. So those facilities have hired staff specifically in the area of quantum computing. They are trying to build up expertise and understand the differences and similarities between the classical HPC that they understand so well and the quantum technology, which has many significant differences. And so I expect over time that the expertise locally within the DOE computing facilities will grow, and as the technology matures and moves more from a basic research, well, this is a fun little processor that we can play with, towards something that you might actually use for computational science, those two sides will merge and integrate.
So maybe just a follow-up comment. In the area of quantum simulation, DOE also has some of the most important use cases, things like lattice gauge theory and so forth, that are also drivers of the HPC centers. I think if you look specifically within those application areas, we do have quantum simulators that are powerful enough today to actually be making a difference, and I think that might be interesting for DOE to look into those kinds of opportunities.
Yeah, so if you look at our quantum centers, SQMS and QSC have strong efforts in looking at that type of application, and SQMS in particular wants to develop a small quantum computer specifically co-designed for HPC applications. I think it's important to recognize, though, that we still have a lot to learn about what quantum computers actually bring to the table for those applications, what algorithms you would want to run, and then understand what resources you would need in order to do so, right? So everybody knows that if you have a very, very, very large quantum computer with fault tolerance built in, you can probably make progress on lattice gauge theories. It's unclear what you can do, what the path towards that is, and what the actual resource requirements are for making progress on scientific problems of interest. So we actually have quite a few people, some funded directly through our high energy physics and nuclear physics programs, and many funded through a couple of our centers, looking at exactly that problem to make sure that we understand the quantum computing resources that are truly important for advancing the DOE mission, and making sure that we have a roadmap to get those resources in place when it's, technically feasible.
Great, thank you very much.
Thanks for your talk here. would like to know if you have research about new mathematical approach to quantum simulations of quantum circuits, because it seems to me that there is a basic assumption on the idea that if you learn and you try quantum algorithm on small circuits, large scale, because we don't have yet large scale quantum computers, this will give us an expertise to get useful quantum circuits, quantum algorithms. This is a basic assumption, and I'm not sure this is true, because when you take, for example, the quantum Fourier transform and you implement it, I showed you here an idea of how to simulate it. It's clear. It seems it's clear that there are patterns that happens in large-scale quantities of qubits that are not present when you make simulations about small scale. So my question is, do you have research about mathematical alternatives to understand what's going on quantum algorithms?
We do. So I think that question is a very important one and something we're going to continue to need to study for quite some time. So we actually have quite a bit of work at this point trying to understand how do you identify whether an algorithm is scalable and what the scalability will be, how to assess whether a kernel of an algorithm that you run on a small quantum processor will how you use that performance to predict performance on a larger quantum processor. We also have a nice research result out of Sandia. I'm not sure if it's published yet, but people were looking at the difference between NISC algorithms, right? Algorithms designed for noisy intermediate scale machines, and the differences between what you optimize if you want your algorithm to run as well as possible on a noisy computer without error correction. And how do those compare to algorithms that you would run on a fault-tolerant machine? And so what they found, and it wasn't particularly difficult to find this, but you did actually need to sit down and ask that question and think about it, is that fault-tolerant algorithms and efficient fault-tolerant algorithms look very, very different than the algorithms you would run on a noisy intermediate scale machine. So I think we do have lots of people looking at this sort of thing, really trying to understand the scalability of algorithms sort of in a theoretical sense and also on the hardware side, right? Because whenever you build larger hardware, you discover more technical challenges that you need to solve, some of which you didn't predict. So I think, we do have quite a bit of work around the topic that you raised, and I expect that we will need to continue to do more work on that in the future.
Thanks.
Hi, thanks a lot for the talk. This was very interesting. I had a question, so you say you have high-performing computers, and there's a lot of research going on quantum algorithms, and that will be useful for the NISC era. So I have a question that is there any research that is going on for quantum-inspired classical algorithms? Like, I've seen some algorithms that use tensor networks to mimic the quantum advantage, but in a classical algorithm. So, is there any research going on in that direction?
So we do not have any formal programs looking at quantum-inspired classical algorithms. We have found that our researchers, so we do. We tend to give our researchers a long leash. We don't hold them to a tight schedule of milestones and deliverables. And what we found is that in the course of their exploration of quantum algorithms, they sometimes find classical algorithms, and we give them free rein to explore those and develop those. But we don't have a formal research program in that area right now.
Thank you.
Hi, I wanted to know what are the formal mechanisms for international people to access some of these, test beds? Yeah.
So I didn't hear the first half of your question.
Sorry. The mechanisms, what are the mechanisms for
Yeah.
accessing as an international person?
Right. So the mechanisms are the same for domestic and international applicants. So for our user facilities, there's a formal application process, and there's usually, for each user facility, they have a different annual cycle. I know the leadership computing facilities have a call for what they call insight proposals annually, and you just submit an application and you're considered along with anybody else. For the test beds I mentioned, there's no difference between being a domestic or international applicant, and you just submit a letter of intent according to the instructions on their website.
So is there any point of contact or any websites that we could access?
Yes, there are lots of points of contact and lots of websites. So if you want to find me afterwards, maybe you can tell me which specific resources you're interested in, and I can help you.
Okay, thank you very much.
All right, great. Thanks, everyone. If everyone could just grab their seats. We have a very special guest with us right now. We're honored to have Representative Brandon Williams join us. He's our representative here in New York State 22nd Congressional District. A little background on Representative Williams. He has a Bachelor in Arts from Pepperdine. He then went on in 1990 and volunteered to serve as a nuclear submarine strategic officer. That was while in college, and in 1991 joined Navy through officer training school, had a great career in the Navy. And the real reason we really like having Brandon involved in our events is he's a true innovation pioneer. He went on to form and start up a software company. He has a deep background in information technologies, including cyber and embedded computing. And of course, quantum fits right in there as well. It's been only his first term, but it's come up to speed so fast and been a strong supporter of quantum. So we're very honored to have him at AFRL today as well as at our event. So Brandon, thank you so much.
Thank you so much. Hey folks. Yeah, I'm from Washington and I'm here to help, in case you haven't heard that one today. So I am new to politics, and I'm certainly new as a member of Congress. But I come out of the tech industry. So if you want to talk about, cloud infrastructure, tier 1 telco infrastructure, edge computing, any of those kinds of things, I'd much rather talk about that than Congress. But one of the things that I enjoy doing is trying to understand how Congress can play a more constructive role in guiding our resources for the things that we need to succeed as a nation, to lead as a nation, and to defend ourselves. And there's nowhere in my district, certainly, and I think few places in America where that is more relevant than right here at Griffiss, right here at AFRL Rome. So because I'm the only nuclear engineer in Congress, and come out of the tech industry, there's a handful of other folks serving in Congress that do have a technical background. If you don't know Congressman Jay Obernolte, I encourage you to make sure that you're aware of him. He went to Caltech, co-founded a software company, is also on the Science-Based Technology Committee with me, and is very conversant in the things that matter to you. So I would commend Congressman Obernolte into your network of folks that you want to know. But I do want to just touch on, you already know the reasons that quantum computing and quantum networking are critical for us. And you're exploring the applications, both commercial and government related, that's going to make that make that successful, make that a great tool in our society. But one of the reasons we're all gathered here is because it's also a strategic issue, that leading in quantum computing or quantum networking is not optional. It breaks encryption, for example, as you all well know. That you can model things that HPC simply can't do today, or other supercomputing compute clusters simply can't do. And with that comes tremendous opportunities for good or bad in our society. And so the United States leading in this field is something that I focus on, and something that I'm here to help AFRL in their mission. So one of the things that I get to do is to make sure that the mission of AFRL is understood and known inside Congress, that gets translated into the appropriations process, that they get the resources that they need. And I'm happy to report that at least through the first pass through the House of Representatives, the resources focusing on quantum, and specifically through AFRL, look to be growing significantly. Now, we won't know until it completes the process, but in terms of a first gate, I just want you to know that we have been very successful in conveying the importance of the mission here and steering or influencing the appropriations process to give you every resource that you've asked for and more. So we'll be paying attention to that process, because it is a process, and DC is a complicated place. But I just want you to know that we're on the front lines of that. As mentioned, I've spent most of my career in technology, both as supervising the operation of nuclear power plants on submarines, or being responsible for strategic missiles on submarines. But even in the civilian world, as I mentioned, focusing on the convergence of IT and OT technologies, modernizing the compute for industrial process automation, which some of you may know. And it's really with that background, up until about a year ago, before I was really committed in earnest to seek this office, that's really what I immersed myself in. So things like cybersecurity for industrial is something that I'm concerned about, and it's something that I know about. How we deploy artificial intelligence and where is something I was working on before I ran for Congress. But in many ways, none of that matters nearly as much as quantum computing. And the potential to have orders of magnitudes of increase in computational capability. We don't even have software designed to take advantage of that. So what you're doing is critically important. I sit on the Science, Space, and Technology Committee, as I mentioned. They made me chairman of the Energy Subcommittee on the Science, Space, Technology Committee, and so I get a lot of the future of energy and a lot of oversight over the Department of Energy labs, including Brookhaven, where I know that a lot of quantum research is taking place. So if my office can be a resource for you, if there's an opportunity to learn more about what you're doing, about the status, about breakthroughs, I can tell you that I'm very interested in that from a technical perspective. I'm told that many of you may know Paul DeBar, former Undersecretary of Department of Energy. Well, Paul and I actually served in the submarine force around the same time. I think he was just a few classes, a few months ahead of me. And so he and I share a training background, and oddly enough have ended up both being connected to the quantum industry and quantum initiatives. So again, my priorities are providing the resources for AFRL, for championing AFRL and the activities that are taking place, but it's also more broadly to understand what you're working on, and to genuinely be there to advocate for you and to communicate to other members of Congress, maybe translate, if you will, some of the work and priorities that you have into action both as a policy as well as an appropriations outcomes that could have very significant impacts on your business. So again, my name is Brandon Williams, and if there's a way that that my office can be helpful, certainly the folks here at AFRL know how to get in touch with me. If anybody has a question, I'm happy to answer any questions. But other than that, we'll actually get on to the important presentations that Dr. Hayduk mentioned before, because I'm not it. So, any questions? Yes, sir.
You're our advocate in DC, and thank you very much for that. But how can we help you, right?
Yeah, it's a good question. You know, I'm a prisoner of my training, and I can say that with some actually pride, because I suspect most of the audience is similar. My engineering training requires that I build a functional model in my head before I can be an effective advocate. And so I've already tortured a number of quantum technology companies and their CTOs on how it works, why it's important. And I have a working framework. You would not hire me to do any research for you. But I tell people, and this is the answer to your question, you have to educate and advocate. So if you think that I can be helpful, do not think that I will know that. One of the things my dad told me growing up, which maybe explains a lot actually now that I think about it, he said, no one is thinking about your future right now. Can't tell you the scars that causes, but this is, causes, but this isn't the place for that. But in sincerity, I think it's actually a very good tool and framework. No one's thinking about your career right now. No one's thinking about your company right now. No one's thinking about your research project right now other than you. And so if you are not advocating and educating, if you assume that somehow I know what you need, you're really making a big strategic mistake. So I tell everybody, never underestimate my ignorance, and advocate and educate at every opportunity. It's the only way to get what you want. It's the only way to get things to move forward. And it's not possible in all the things that I in my office that we're trying to do. There's no way that I can to know what you need. So that responsibility is on you and exclusively on you. Thank you for asking. Please, any other questions? Great. All right. Thanks so much, and thank you so much for attending.
So on behalf and from the Griffiss Institute, here's an Innovare Advancement Center pin. Yes.
Thank you.
Thank you. Thanks for coming.
You bet. This goes right underneath my SSBN Strategic Deterrence pen, which has never been worn in Congress before. Right? There's never been another one like me in Congress. And if you know any Navy nukes, you know why that's true. They couldn't win an election. It's not possible.
Thank you. Thank you. All right, what a treat to have Congressman Williams here. So next up, we have Ms. LaVida Cooper. She's the Deputy Program Manager of Strategic Initiatives for Exploration and Space Communications Project Division at NASA's Goddard Space Flight Center. She also serves as the Executive Director of the Washington Metropolitan Quantum Network Research Consortium, also known as DCQNET. Please give her a warm welcome as she tells us and enlightens us about the happenings with the DCQNET. LaVida.
Okay, well, good morning, everyone. It's a pleasure to be here, and I'd like to thank those at AFRL for extending the invitation. So as Mike noted, I'm here to talk to you all today about the DCQNET. It is a consortium, essentially, that is keenly focused on regional quantum networking being essentially represented through a testbed and building up testbed infrastructure in the DC metropolitan area. So before I go into the specifics of the consortium, I will go through a bit of a snapshot of the landscape. Everything that we've heard between yesterday and today has helped to kind of bring all of us up to speed in terms of how things are really dynamically moving. And so whenever I give a talk regarding the DC QNET, I like to kind of just hit a synchronization pulse, if you will, to share, you know, where we are and some of the things that are really guiding some of the priorities and/or challenges that we see right ahead of us in terms of the portfolio of work or some of the enablers that the consortium sees that it can take advantage of, frankly. So from a national perspective, we actually just heard a lot of excellent input from the congressman that I was going to touch on as well. We're seeing a wave of activity with many accomplishments, as well as grassroots cooperation, collaboration, and also top-level coordination. And all of it is coming together in such a way that we really are starting to see a nice improvement, also sustained improvement in terms of our QIS capability here within the United States. In fact, actually just this month, earlier this month, the Quantum Initiative Advisory Committee released a report of recommendations to help guide essentially the content that would be comprised of the reauthorizing of the National Quantum Initiative. A number of those items are intended to really help accelerate beyond the progress that we've seen over the last few years, where the country has made great strides, as you've heard from many of our speakers across industry as well as government. So that was really important, and organizations just like the consortium, the DC QNET, as well as many others, take a lot of those recommendations seriously and also do what we can to help amplify them. One of the items that we also saw this month that was really positive for the QIS community nationwide was the hearing that was held on June 7th. Essentially before the Committee on Science, Space, and Technology with the U.S. House of Representatives. And so that was essentially an opportunity for many individuals across even the private space, public space, in addition to researchers, to really put into words what that recommendation, set of recommendations from the report from the advisory committee wanted to see inside of the reauthorization. So in fact, actually Paul DeBar, that was referenced earlier, was one of the key witnesses there, in addition to Charlie Tahan and many others. And so there was actually a lot of positive interactions. For those of you who did not see the full video of that hearing, and many of the recommendations, it looks like will ultimately end up making it in to the reauthorization, but it does have to go through a process. One of the key things that's important to the consortium that I'll be talking to you about next here is the fact that they're talking about expanding the number of departments and agencies that are going to be included in the National Quantum Initiative. This is not because they're just looking to give everybody a golden ticket, but it is essentially driven by the specific mission sets, capabilities, and/or infrastructure of specific departments and agencies and communities, federal communities, that they're looking to see included. So for example, some of the early research done by the IC community is being advocated for the IC community to be included. NASA is also being referenced as another agency to be included, as well as many others. On the quantum sensing front, to hit the second bullet here, as you've heard again from many of the folks here today, this is an area that is continuing to flourish. We're seeing lots of new devices, components, as well as applications expand by the day, and it's really, really exciting to see. And so as we move on to talk about the third bullet there with quantum computing, you heard excellent examples and context and landscape from our previous speaker with Claire from the Department of Energy. And we're also seeing steady progress across everything from basic research as well as the lab to market space, which is extremely important. So I know that some people, many people, may have heard some of the talking points about is quantum computing essentially being overhyped, because we're seeing a lot of activity and investment from the VC and or venture capital community. But regardless of where you fall on that side of the argument regarding quantum computing, one thing that we know and that we can see for sure is that there is real progress being made within quantum computing. There are real devices, real products, real hardware, and real results that we're all seeing every single day. New companies making actual progress, infrastructure, as well as getting more and more customers as well as we move more of this technology from lab to market. And so we're excited to see that progress and looking for ways in which we can leverage that. One of the things that we also hear sometimes regarding quantum computing is the application space. And so within my home organization of NASA, one of the things that we're doing specifically coming out of the Ames Research Center in California is we have the Quail Lab. Some of you may be familiar with the Quail Lab that focuses on quantum computing as well as AI. And they're specifically looking at NASA mission use cases regarding our data processing needs, where we know that we will soon start to bump up against the processing capacity of our supercomputers. And so we are actually acting as anywhere from alpha to beta testers in collaboration with in collaboration with a lot of the quantum computing companies and national laboratories, so that we can start to realize and understand just how applicable these quantum computing assets will be to our future mission within the NASA mission data processing arena. And so last but not least, just to touch on quantum networking, just from a national landscape perspective, this one is most exciting for me. We see all manner of test beds popping up across the country. You've even heard about some of them with some of the previous speakers. We continue to see very broad development in this area. We're also seeing, and this is extremely exciting for me, lots of lessons learned coming from even the classical networking community, but then being adapted to be applied to quantum networking. So many of you probably have heard or read papers, or even you're thinking about it yourselves, how, for example, the classical network layer model and approaches can be either expanded or amended to start to accommodate some of maybe our needs that we may need in the future in terms of quantum networking. Some of the other things that we're starting to see as well is there's quantum networking, but we also have insight into how quantum can help augment classical networking and classical communications. And so there are teams of folks that are looking at even how some of the quantum components and or quantum devices can help with just singular actual classical communications functions to help them be more efficient and or to improve some of the key parameters there. And so, whether we're talking about actual terrestrial and or space-based quantum networking, we're seeing a lot of progress there. From a challenges perspective, one of the things that really kind of keeps me up at night but also helps me to wake up in the morning is really thinking about how can the United States, demonstrably bring all of this innovation and progress together. There's pockets of progress and results that's happening essentially across the QIS landscape. However, we have yet to see, for example, say maybe a space-based quantum networking or quantum communications demonstration, for example. That is something that is actually led by the United States, that's on the cover of magazines and essentially being talked about in some of the recent publications. And so that is one of the areas that the DC QNET, as well as many of our partners, are looking to see if that is a challenge that within the near term, and then by having a means, by building on any near-term progress there, that we can continuously kind of build from there to help sustain some American leadership demonstrably at scale within that realm. And so looking at things like having a crawl, walk, fly mentality to making progress is actually where having partners such as AFRL, who is an associate member of the DC QNET, really comes into play. And so centers like the Innovare Advancement Center here, where we can have the international collaboration on the basic and theoretical research related to quantum, but then once we get to certain maturity points, we can take that and bring that into some of the government space where maybe it may not be as public, but it is advanced to a point where we can really start to become a lot more mission-specific, application-specific, is very enabling. And so as I look at some of the future enablers, again, the lab to market space is very exciting because we need real products as we start to look at things like integration and operationalization for real life use cases and applications, and building up test beds such as the one that I'll talk to you about. Also, in terms of future enablers, it's really exciting to hear how almost every speaker, as well as folks that I've talked to on the sidelines here, have really leaned into thinking about use cases and applications that really form the base of operational scenarios to be pursued. I think that pursuing what I like to call the low-hanging fruit of some of these operational scenarios is really where, from a national perspective, getting to that demonstrable near-term application is where we'll ultimately have our salvation. And so leaning into operations and also systems integration, I think, which has always been a strength of the United States, which speaks to the multidisciplinary effort that this really is where we need to go. And so with that, being a bit of a sort of snapshot of elements of the landscape that helps set sort of the foundation for the types of activities that we're doing within the consortium, now I'll tell you a bit about the DC QNET. And so the DC QNET is, as I mentioned, a consortium. We're mostly centered within the Washington, D.C. metro area. We consist of 6 federal agencies and departments with also some out-of-region affiliates, meaning folks and organizations that are not local to D.C., but still we have common research interests, and that brings us together. And so the primary objective of the organization is really to move towards the creation, development, as well as the demonstration of a regional quantum networking testbed. Some of the things that we thought in terms of principles that we wanted to see within a testbed that would enable each of the 6 members, as well as any other users of the testbed, to be able to take advantage, most advantage for their needs, is to have an open environment that was non-proprietary, that we can really use to do agile testing of everything from protocols to changing and evolving architectures, as well as various components, again, given the application and scenarios that they need for their specific department or agency mission focus. The other thing that the other item that is a goal of the consortium is essentially not just to ensure that we have a test bed for individual mission enabling experiments and demonstration, but actually to be able to enable, cross government synergies as well as demonstration and research, and that's exactly what we are starting to see within our members. And so here's a list of the members. We have The Army, known as DEVCOM, or Army Research Laboratory, located in Adelphi, Maryland, for those of you that are familiar with the D.C. Area. We also have the Naval Research Laboratory from the D.C. area. We also have the U.S. Naval Observatory, and one of the key items that we relish in having the U.S. Naval Observatory as one of our members is that they are the DoD's timekeepers. And so they have a rich history regarding timekeeping, precision timekeeping, distribution, and so that really is something that they bring as a unique capability to the consortium. In addition to those three, we also have NIST, who again is also another organization that is very interested in time, as many of you are aware. And so by having both USNO as well as NIST within our ranks, we really do have a focus on metrology as well as exquisite timekeeping and synchronization. In addition, we have the National Security Agency as well as NASA. And our two out-of-region affiliates includes the Naval Information Warfare Center out on the West Coast, in addition to here in Rome, New York, AFRL. And so just to get a little bit of insight into how we're organized here, I serve as the executive director, but most importantly, we have our executive steering committee. And so that is comprised of having at least one senior executive from each of the 6 agencies. And what that means is that whenever we need to pull on the resources and or set priority objectives and goals that really align with a specific organization's mission, that we have a senior executive there so that we can essentially make decisional progress very, very quickly. And it's really helped to accelerate standing up our infrastructure. And so we've been in existence since May of 22. So again, some of the key attributes here is that we do have only federal employees. And so one of the things that allows us to do is not only can our federal departments and agencies work on their approved programs that they're authorized and funded for, but they can also now work together to formulate what we like to call pre-decisional programs. So if there is something that they would like to influence for their next funding cycle, new technical objectives and goals that they want to start to get out in front of, maybe get early data for that so they can make the case to their senior leaders and or even Congress, they can use this platform to do that. In addition, one of the things that we think is very important is to make the technology and its application and usefulness real for regional lawmakers. And so by being in D.C., having the infrastructure, the hardware, all accessible between D.C., Maryland, and Virginia for lawmakers to come and see what they're investing in, get demonstrations, be educated, if you will, that is one of the exact reasons why we exist, in addition to loving the work that we do. As I noted earlier, we believe that timekeeping is going to be key, and so we lean into that in terms of understanding that it's likely a prerequisite for high-fidelity quantum networking applications, experiments, and demonstrations. Lastly, here I'll just pull on the thread that the metrology work that we do, we also believe that it's a precursor in terms, again, of the fidelity of the experiments that are executed ultimately within the network. So here you can kind of see a little bit of some of the synergistic areas where we have both NIST and USNO focusing on metrology, focusing on the timekeeping, and there up top we really do start to see within our working groups, especially as experiments are formulated, that all 6 of the organizations plus our affiliates are all working together on all manner of experiments and applications. And then lastly here on the bottom, one unique intersection that we have is that we are ultimately a place where all of our DoD contingents have a unique quantum networking test space for any DoD-specific objectives and goals that need to be demonstrated. So some of the key activities that we're involved in right now is we are focused on essentially defining, growing, architecting our regional quantum network such that we're supporting the quantum initiative and the development of right-sized quantum networks. And so presently we have about 260 kilometers and growing of essentially distance in terms of our network, and we've got a minimum of 4 access points presently that are operational and growing. And so we really are looking to essentially evolve that such that our extended operating capability and architecture meets, again, the needs of our portfolio of experiments moving forward. And so looking here towards the bottom of the slide, in terms of enabling components as well as devices and items where we're focused at a smaller scale, just as many others that are in the field right now, we're looking at everything from single photon sources and detectors, and because of the heterogeneous mix of, again, mission sets and organizations, they are explicitly looking at devices that help them to meet their mission needs. So there is actually quite the diversity in terms of the types of sources that are being pursued, as well as detectors that are being leveraged within experiments, as well as demonstrations. Quantum memories as well as repeaters are a focus. We continue to essentially monitor and watch the repeater development, as many of us look for the maturation of repeaters, but at the same time there are individual organizations within our ranks that actually are pursuing quantum memory development themselves and or leveraging quantum memories that have been developed, for example, by FFRDCs and other national laboratories. And so those things are quite important to us in some of the scenarios that we're looking to execute. Entanglement generation and generation and storage is, of course, of keen interest to anyone within the quantum networking realm, as well as quantum frequency conversion. Again, as you can imagine, with all of the various application spaces, the various infrastructure that spans a minimum of 6 different organizations, when we, say for the first time, started to just query our members on, okay, what frequencies, what colors are you guys working at or looking at, the spreadsheet was quite long. Okay, and it's not because folks just like necessarily, spanning, a wide range there, but it really is because it was driven by their unique mandated mission sets for their organizations. And so having a robust and very deliberate approach to frequency conversion is actually the first step for us in many ways to help ensuring things like interoperability when we go after specific demonstrations and experiments that are synergistic in nature, where we're sharing resources as well as collaborating on a specific objective. In terms of the infrastructure, looking at quantum networks, so we presently are a terrestrial-based quantum network. We use and lease commercial fiber in the DC metropolitan area. So things like making sure we have well-characterized fiber where we understand the losses, we understand and we have evaluated the stability of the fiber that we're leveraging, as well as then even leaning into defining and even understanding the results regarding stabilization techniques is something that is that we're all keen to do, and it's ongoing work for us, especially as we continue to expand the architecture and the overall span of the network. Transduction as well as synchronization, time synchronization, is key, as well as having within our ranks a set of members that are keenly interested in things like emulation, modeling, and simulation. Just as a general note, in terms of quantum networking, I would venture to say that we probably don't have enough maybe focus in this area. And when we look at how emulation, modeling, and simulation have served us classically, I definitely would like to encourage within the realm of QIS and quantum networking specifically for those of you who are interested in that sort of thing to definitely lean into it. because it's definitely needed. And so beyond emulation, modeling, simulation, understanding free space links, making sure that we're taking advantage, again, of the classical advances that we're seeing within optical communications, where we have actually multiple members within the DC QNET presently that have made advances within showing that optical communications is not just a quote-unquote new technology, but it's actually an operational capability that's been demonstrated over the last decade and proven to be essentially something that can be leveraged. So ranging from the Naval Research Laboratories optical communications demonstrations, as well as at least a decade of demonstrations of space-to-ground, free space optical with NASA demonstrations, with the laser communications demonstration LCRD mission actually being operational right now. In addition to, there's the T-Bird terabyte infrared demonstration for optical communications that recently just broke a record with 4.8 terabytes of data being transferred within a single pass. And so we know that we have a capability there to build on, and we're looking at ways to try to leverage that in the future when it comes to expanding our infrastructure. And so understanding things like architecture, how to evolve the architecture, how to characterize the architecture, how to understand the translation of some of our classical terminologies, but adapting it again for the use cases within quantum in terms of the types of services and or understanding the state and the status of the network, learning essentially how to make sure that we are orchestrating a network appropriately and managing that network and the access points, the resources properly, are all things that from at least an infrastructure standpoint that we're looking at. So network management is a key piece of how we're building up the network with these items in mind. And then some of the early stage experimentation that the consortium is moving into, of course, includes leveraging both a classical control plane as well as a quantum channel. And so beyond just working with ourselves and communicating with those within the consortium, we do actively go out into the community, the QIS community, research community, to present results, learn from the community so that we can bring those items back and apply them within our infrastructure. And so here is essentially a depiction of what we view as our present experiments ecosystem, if you will. So everything is represented here that I kind of talked about earlier, where it ranges from essentially understanding that we're looking at things like memories, all of the emulation and simulation aspects of that. We're also essentially looking at things like the classical phase and polarization control, to the free space experiments for air-to-ground orchestration being there, in addition to just classical meat and potato items, is making sure we have a well-characterized link, as well as the frequency conversion. And so we do pursue a lot of this work in multiple ways because we have such a large swath of researchers and scientists that span multiple organizations within the government. We've organized ourselves for now into at least 3 ad hoc working groups. Our largest working group is our experiments working group, where we have a very motley and robust conversation of sometimes up to 40 or 50 scientists and engineers talking about and defining experiments that they need to do just to execute their basic missions, but then also finding those synergistic points where, when someone over here talks about the timing, precision that they need for their mission, and then they hear from 2 or 3 others that, oh, I'm doing that and I've already made, progress in this way. This is how we're able to actually bring best value and accelerate some of our time frames, for example. Again, here we have a fiber network evaluation and stabilization working group. So this is really where you would imagine, you walk into the room and you see a lot of our network guys, right? A lot of our classical networking folks that have been doing IT and networks within the government, but also combined with some of our physicists that are really looking to make sure that the baseline infrastructure is well understood and that is and that it is essentially driven by the experimental objectives coming out of the experiments portfolio. And so the requirements and desirements that come out of the experiments portfolio as it was defined, our fiber working group essentially takes that to make sure that we have the capacity, the number of access points, that we have the ability to orchestrate the network and within the way and the means that essentially our experiments require. And so last but not least, we have our interface specifications working group. And yet again, this is another team of folks that's, again, span multiple agencies that take into account the key requirements of targeted experiments and demonstrations, but they're really actually thinking about the interoperability of it. How can we bring it all together in a standard way such that there's a standard set of rules for how we're going to go about executing that. And so these three are what we have presently, and we're in the middle of actually standing up a timing working group next because, again, of the demands that we're starting to see come out of the types of experiments that are being formulated presently for near-term execution. And so here I'm just going to highlight a little bit of some of the research that's come out of the group across a couple of our organizations. And so here on the first line here, we can see we have an experimental demonstration regarding coexistence. This comes from one of our, a cross-section of our researchers actually from NIST, where essentially they're reporting within this publication that they have demonstrated polarization entanglement distribution as well as precision timing synchronization protocol between two nodes. For now it's just 250 meters, but they did that using a single fiber carrying both quantum and classical data. For those of you that just want to understand maybe some of the goals and objectives that are unique to the DC QNET, in addition to wanting to build up the infrastructure, exercise that infrastructure, there is actually a bit of an obsession with essentially trying to prove out and demonstrate coexistence at longer and longer demonstration distances. And so if anyone here has a common interest in that, I would encourage you to actually follow these authors here because you can expect more publications from them in that particular area. On the bottom half here, there's actually a publication that's come out of the Naval Research Laboratory ranks of the organization with essentially some of the sensing and interferometry work that the NRL is known for. And so we look forward to seeing their continued advancement in the area of quantum sensing because, as you know, quantum networks essentially can be great infrastructure essentially for future distributed sensing as well as distributed quantum computing applications and use cases. And then here we actually have a couple of highlights. I'll just go through, I think I can touch on, I have enough time for both of them. So with the first one, we actually have something from AFRL, our Army Research Laboratory. Researchers, Dan Jones and Brian Kirby, where with them being specifically kind of motivated for error-free quantum information transmission, they present two specific examples and cases where they've seen actual promising outcomes with some of the methods that they're looking at. And then also here on the bottom, another example from the from our folks here within NIST. That where they're really leaning into having low-cost, affordable, portable infrastructure that can really help enable the types of capabilities that are existing at some of the access points and nodes within the network, where they've actually come together to pull together, I think it's about the size of a half rack or less, essentially a means by which we can use their source and receiver to generate root and essentially measure quantum states with the specific asset that they have, which can be deployed across multiple nodes within a network. And so the key thing there, which has been really great for the consortium, is that with NIST baselining that bottom what I'll just call asset, this is something that essentially all of the organizations within our consortium are looking to build up and deploy throughout the network. And so here's just from a high level some of the technical objectives that we're marching towards within the consortium. So within the near term, as you've heard earlier, we're looking at characterizing our fiber and executing basic networking experiments. This is ongoing. In fact, I would say in many ways the team is ahead of our roadmap in that regard. There's quantum interference demonstrations that are being executed as well by the team, as well as the team going out to pursue entanglement demonstration between nodes. And so before I left to come here, I received an update essentially on some of the pre-formulation experimental activities that the team is going through with defining actually one of their next entanglement demonstration experiments. Over the long term, we look to expand our network in a very application-specific, intentional way, again, to enable the missions of the organizations. So we acknowledge and we actually lean into the fact that we have various access points that help to bring about a heterogeneous mix of capacity as well as capabilities, which then helps to essentially diversify the types of experiments and research that can be executed within our regional test bed. And then here, the last bullet really speaks to understanding that we don't want to remain just an insular regional quantum network test bed. We're aware of and we're extremely energized by the progress that we see across the country with other regional quantum networks popping up everywhere, across the eastern seaboard. We see them in the Midwest, we see them in the far west, we see them in the south, and so we're actually in close collaboration as well as coordination and discussion with multiple other regional quantum networks with the hopes, essentially an objective of actually defining how we can interconnect each of our quantum networks so that we can start to make what I like to call, again, the low-hanging fruit stepping stones towards intra-continental entanglement distribution. So to kind of bring it up a level to a policy standpoint, going back to some of the early documents that we saw showing up on quantum.gov, where there were national objectives regarding quantum networking articulated, things like intracontinental entanglement distribution showed up on those documents, right? We saw in 2019, 2020, where NASA, collaborating with many other government organizations, formulated actually an intra and intercontinental space-based quantum entanglement missions for consideration by the executive branch. None of those have yet to be turned on. However, as I've spent time within the DC QNET consortium, as members have talked amongst themselves as well as talking with other leaders with other regional quantum networks, one of the things that we are starting to see a lot of synergy on is that actually we can leverage the investment over the past 5 years in these regional networks to serve as a foundation for achieving potentially the intracontinental entanglement distribution or quantum networking goals by using these networks as maybe the backhaul and or locations where we can place ground terminals, telescopes, access points, many of which already have those types of assets, seeing assets within reach that can be combined with things like small sat technologies depending on the types and scale and size of the payload that you need for a flight asset to enable these higher level policy goals here and now. And so we're actually looking at proposals and having those discussions here in what we call the fiscal year 23, so that starting in calendar year 24 that we can start to move towards actually integrating and executing potentially one of these scenarios that are being studied. And so I believe that's my last slide. So are there any questions?
Thank you for your talk. You mentioned secure quantum communication. Do you have any prospects about quantum key distribution protocols also?
As many others have eloquently essentially talked about how the NSA has, how can I say it, characterized QKD, if I heard you correctly. We are not necessarily within our experiments portfolio presently seeing a lot of folks propose experiments regarding QKD. But with that being said, we do understand, frankly, that QKD is still a tool, right? A tool for learning, understanding. We see where it's showing up within the marketplace. And so it's not necessarily a posture, at least within our consortium, of ignoring it. There are those that are pursuing and looking at it for knowledge gain on the side. However, in terms of our formal portfolio, we're not necessarily pursuing that because since we are all federal entities, we have to, definitely comply with that broader government guidance. Does that answer your question?
Yes, thank you.
Okay, thank you. I see another.
Yeah, given that DARPA is proposing to use DC QNET for a proposal that starts in January of next year, how confident are you that additionally that project proposes fiber characterization, entanglement distribution as fundamental components of the project? How confident are you that the network is ready to go for project folks to execute?
Yeah, so great question, and because we've had a long runway essentially with working with DARPA to get to that public announcement, we're pretty confident. We've been, many of us, doing this prior to the MOU being signed in 22, and so there's, as I noted, there's a nice run of fiber that's being exercised operationally, as well as multiple nodes, and we've already got a baseline essentially for what I would like to call a subnet that we would use essentially for DARPA's objectives once DARPA's done with their selection process, et cetera, and we know who we're dealing with and what their specific experimental integration and demonstration needs are. So excellent question.
I have a follow-on. The multiplexing that was done between classical and quantum, was that temporal, spectral, or spatial?
Maybe let me talk to you offline about that. I can probably put you in contact with one of our scientists.
Yeah, thank you.
Okay, no problem. Okay. Oh, one more.
Thanks for your interesting talk. Have you developed research about a different notion of entanglement specifically applied to networking? Because I watched yesterday some talks about quantum networking. I'm not a specialist in that and try to understand at night. And I saw that you have been using the regular notion of entanglement in terms of separability of the stating of the basics. But if you do that, you are losing important information about the topology, the configuration of the networking. You are losing important information about directions to improve the experiments. So my question is, have you developed a kind of topological notion of distributive entanglement?
So many of those within our experiments group are actually talking about that. I try to, for these general talks, be at a higher level of abstraction, but actually, yes, many of our team members are, they're aware of the various types, right, of entanglement. They're actually looking at, again, from even a network management standpoint, how to make sure that we're preserving, understanding, we're getting the insight that we want to be able to pull out of the different types of experiments that we're doing. So actually, I'd be happy to connect you with some of our researchers as well, because I think they would love to have, and maybe, an exchange with you to go a little deeper on the conversation. So I'd be happy to, make that connection.
Okay, thank you.
Okay, thank you. Okay, I think that's it.
Anyone else? Nice call.
Okay.
All right.
Okay, thank you for your time.
All right, excellent. So that draws our morning to a close. We're going to reconvene here at about 1:15, and then we'll go to our breakout sessions. So Jim's going to talk about lunch in a second. I'll call him up here. But as you go through lunch, think about what breakout sessions you want to go to and start formulating, maybe some of the points you want to bring up or some of the questions, because I know our moderators and facilitators are ready to go.